So I've always been puzzled about algebraic K-theory. And this is a little primer that I wrote for myself. It's based on a derivation that's elementary by Hyman Bass. And basically, it describes in elementary terms what K-theory is for K1. You can have it for K0, other integers. And what's nice about it is it's a quite straightforward way of describing this. So let's see how this works. So I'll write here a primer on algebraic K1 theory. So suppose we have a ring R. Then we can talk about matrices that are invertible. So we might have a matrix M in the general linear group over R that has, it's n by n. And we want to define what's called the co-limit of that. And so the idea is that if I have a matrix M like this, then what I can do is I can send that to a matrix that's one dimension higher by taking M like this, putting a unit there or one, and zeros like this. So this is a mapping from GL and R, the general linear group of n by n matrices over R. It gets included into the one that's one up. And in this way, we can look at a network of all of these. We can keep including these and take the infinite limit. And that thing is called a co-limit. And it's denoted GL R like that. And so you can think of this thing as having all these inclusions that are including in the next biggest one and so forth, and all going up like this, and all going out to a limit here. So it means that even if we have two matrices of different sizes, different dimensions, we can multiply them and do other operations on them by going up to their sort of common descendant. So we have this structure here, which is the direct limit of all the GL and R's under the inclusion I, which is this mapping here. Okay, so we have this strange structure here. So what we're basically interested in doing, and this is just an intuition, is we're interested in measuring the extent to which matrices over this ring commute when the matrices are of any size. So this sort of in this infinite limit, this infinite structure. So I want to consider measuring that by computing commutator subgroups. So one way of thinking about what the K1 theory or K1 of this ring is, there are various ways you can think about this. So one thing you can do is you can take this infinite object here, GLR, the co-limit, and you can do what's called abelianizing it. So turn it into an abelian group. So how would you do that? You take GLR and you mod out by the commutator subgroup. So what's the way to think about that? That's the same as GLR when you mod out by the relationship AB minus BA. So the extent to which things don't commute. And incidentally, this thing here, in terms of notation, this is called the commutator subgroup. And it's also called E of R which is called the Whitehead group. So what you're basically doing here is you're forming these this infinite set of matrices of any finite size, and you have a structure in here where you can still multiply them. If you have two things of different size, you can take these chains, put them together in some compatible higher dimension, and then you can multiply them, do other operations on them, which is great. And what you're basically doing in this construction called the K1 theory, or the K1, is you're measuring the extent to which matrices over R do not commute. So what are caveats? This only addresses K1. So what about K0? What about K2? These are all defined mathematically, but we might want to do that later. And finally, the definition is very operational. It's how we set it up for this particular case. Okay, so maybe that's good enough test to see how this is working. And let me know what you think.